Alright folks, today we're going to talk about how to calculate the speed of sound using some pretty simple apparatuses. We're actually going to start out using some tuning forks with known frequencies, and we're going to use columns of water. And there's a little trick we can use with resonance and actually try to measure in a lab setting what the actual speed of sound is. Now, this is obviously something that you could look up, and we probably know what the speed of sound is, and it does vary based upon air temperature and humidity and a lot of other variables that would change air density and so forth. And you guys are going to use some of what you've already learned about the relationship between velocity, frequency, and wavelength. If you can have some measurements of either of those two of those three variables, you should be able to calculate one of the unknowns. So the lab itself is kind of like this. The problem is asking how are you going to do this. Before we get into that, I'll talk a little bit about the differences between mechanical and electromagnetic waves, or longitudinal waves versus transverse waves, because we did mention this earlier on, but kind of a good time to refresh it. So what we have here is a model that's trying to show what an actual sound wave would look like. So if you look at the item that's producing sound here, they show as a speaker, and then the ear obviously receiving. I think sometimes the misconception as we've been talking about waves is that all waves kind of travel up and down in some sort of an oscillating pattern. Looking back at the notes, we did mention that there's a difference between mechanical waves, electromagnetic waves, and then even in the category of mechanical waves, we say that there's types of surface waves, there's seismic waves, and then compression waves or longitudinal waves. So the major difference is the direction that the particles move relative to the velocity, or direction of the actual wave. So from the speaker to the ear, we would say that the direction of velocity is going this way, and the direction of oscillation is in the same direction. It's parallel with the velocity. So traveling from the speaker toward the ear, the wave actually kind of oscillates like this. You see these compressions and what they would call rarefaction, but it's basically compressed and expanded and compressed and expanded and compressed and expanded as it travels through the air. Now, when we use a transverse wave model, which is not what sound does, electromagnetic waves travel this way. They oscillate up and down from kind of a neutral position. There are still similarities between the two. You obviously have areas of maximum and minimum, maximum and minimums, maximum and minimums as you go along. The model that we use for transverse waves in a mathematical standpoint is a little bit easier to observe, because we have like a neutral position and we have maximum and minimums that go above or below that neutral position a certain value. And of course your amplitude would be measured from the neutral position to the top or the neutral position to the bottom, and your actual wavelengths would be measured from a peak to a peak, or a trough to a trough, or any start point back to that original start point. I could start counting here and have it go all the way up and down to here, and I could consider that one full wave cycle. Where when we're looking at our longitudinal wave or our sound wave, if we're going to be measuring wavelength, you're going to be measuring it from maxima to maxima. The change or oscillation between, which is transferring the energy from basically one place to another, because that's really what waves are doing, is they're transferring energy from one point to another. Mechanical waves need to travel through some sort of a median, like solids, liquids, or gases, and electromagnetic waves, they do not have to travel through a median. We can calculate the speed or velocity of a wave if you know the frequency and you know the wavelength. Remember, the frequency in essence is kind of like a time. It's how many times it oscillates in a given second, and the wavelength tells us a distance. So when we look at this, you really have a hertz is the same as 1 over a second, and the meter itself is just a meter over 1. So when you multiply these two things together, you get a meter times 1 on the top, and you get a 1 times the second on the bottom, and you get a meter per second, which does give you velocity. So the objective in the lab is to try to figure out, all right, what is the speed of sound, or what is the speed of all these waves that we're going to produce. On our tuning forks themselves, and we'll go through this in a little bit more detail, but each of these tuning forks has a number printed right on them, and it's tuned to that actual frequency. This tuning fork was at 128 Hertz, which means when I tap this on the palm of my hand and let it oscillate back and forth, it oscillates back and forth, or think of it more like this, compressing the waves toward you 128 times every single second. So with that part of the puzzle solved, all we need to try to do is figure out the actual wavelength. And if we can figure out the wavelength, then we should be able to multiply those two together to get the wave speed. Now here's the trick. We're going to use resonance in a tube in order to try to figure this out. So the diagram that we kind of have here above, we're going to be using a water column and a hollow tube. And the whole idea of this is you can raise or lower the tube in order to adjust the length of this air column. Neutral position to the maxima, which in essence is a quarter of the wavelength. So it's commonly misperceived that the resonance will happen at a full wavelength, but actually it will happen at a quarter, and it will happen again at 3/4 of the wavelength. So because it's got to be at the peak or the trough, so you got to be careful. You'll hear it as it moves up. You'll hear it in different spots. We always want to catch it at the first point of resonance so that you know you're only getting the first quarter of the wavelength. If we can determine that quarter of the wavelength, then we just simply multiply that by 4 to get the full wavelength, and then plug it into our velocity equation. So you will see in the data table, we have a spot on here that labels the frequency of all the tuning forks we're gonna try. The highest frequency being 512, and our lowest frequency being the 256. The resonance length, again, we'll measure in centimeters, which is a quarter of the actual wave length. So whatever we get here for resonant length, we'll multiply by 4, put it here. We're measuring it in centimeters, so we'll have to convert that to meters. And then to actually find the speed of sound, we'll simply multiply the frequency by the wavelength. And then we should hopefully get some answers or results that are pretty close to the accepted value. So I'll collect some of the data. You guys are going to want to record all of it in there and do some of the calculations, and then we'll check to see how close we all were. Alright, we'll take it over to the experiment right over here. Alright folks, so over here we kind of have the apparatus set up. I basically have one column of water in here, and then I have a piece of tube that is hollow on the inside. And this is basically going to be my instant adjustment is to raise and lower this. I'll be changing the length of the air column inside of the tube. The biggest thing we got to remember is when we're measuring or listening for the resonance, when I measure the length of the air column, I have to measure from the top of the water to the top of the tube. So I'm going to start just by example here. I'm going to use the 512 Hertz tuning fork, and I'm going to hit it to get it ringing. I'm going to set it up on top of the tube. I'm going to slowly raise this until I hear the resonance, and at the moment that I hear the resonance, I'm going to stop, and then I will use the meter stick to measure the height from the top of the water column to the top of the tube, from the top of the water column to the top of the tube, and then I'm going to record that inside our data table. And we'll do this across for all of the different tubes. So we'll get this set up here, and you guys can record your data. So here's just an example as to the resonance that we're trying to listen for. So I'll hit the tuning fork, I'll give you a sound of it, and then I'll show you what the resonance is. I'll do it one more time. You hear it come and go when I get right to that height. Alright, so this will be 512 Hertz, and we're going to try to record the resonant length. So our first resonant length there, I'm getting about 17 centimeters. So that's 512 Hertz, about 17 centimeters. Now we're going to go to 480 hertz. I'm going to do the same thing, and this one in theory should be a little bit further away, so we'll hit this tuning fork. Definitely got just a hair more on that one. So I'm looking at about 18 centimeters for 480 hertz. Then we're going to go to 256 hertz. This 256 hertz should be quite a bit longer here. Here it is. So for 256 hertz, I'm looking at about 33 centimeters there. That one was quite a bit longer. And 288. Here we got 288 hertz. It's definitely a little bit less than our 256 there. We're at about 30 centimeters for that one. We got 320 hertz. Hertz, a little bit lower than before. We're at about 27. We're at about 27 for this one. The next one is 384 hertz. So 384 hertz, we're at about 22 centimeters. 428 hertz here is our next. So this should be a bit shorter wavelength. Let's see. So 428, we're at about 20 centimeters. Alright folks, so now that we got some data, you guys should have that recorded in here for the resonance length. I'll repeat the values that I got in case you did not get them, and then I'll just give you a brief explanation on how to do the calculations, and you can go on to answer the questions, and then we'll compare your results to the actual speed of sound and see how close we were. So when we did the 512 hertz, we got 17 centimeters for 480. Now keep in mind, these ones are all in centimeters. We need to somehow get the wavelength in meters. These resonant lengths are 1/4 the actual wavelength. So you need to take this value and you need to multiply it by 4, and then you can move them down here. For example, if we multiply the 17 by 4, for example, you should get 68 centimeters, and then if we convert this to meters, you have to divide by 100, so this will give me 0.68 meters. To calculate velocity or the speed of sound, remember that it's frequency multiplied by the wavelength. So we have frequency up here, which is 512. If I multiply that 512 by the wavelength, 0.68 meters, this gives me a value of 348.2 meters per second. So you guys should continue on, do the rest of the calculations. If you flip to the next page, it will also ask for you to average out the speed of sound. So what you get for those 7 values that we got, you're going to add all 7 of them together, divide by 7, put your value here, and then we'll compare it to the actual speed of sound. Okay? So I want you to go ahead and do that first, do all the calculations, then we'll look at the actual speed of sound. So, time for you to do a little bit of work. Alright, so let's see what you guys got. The actual speed of sound that we're going to go with, the accepted value for the speed of sound is 340 meters per second. Of course, this varies a little bit. Take a look at whatever you got. It's probably pretty close to this, and you can conclude based on those observations. So there's some follow-up questions here, which you guys can go through. Again, if you want to do all of your work on this piece of paper, you can submit it to me in person or photograph it if you'd like, but there will be an online digital submission for this also, where you can just enter in. I'll select some random answers and questions that you guys can input, so just to solidify that you guys have done the lab. So there it is. I appreciate it, guys. Thanks a lot and have a good week. If you have any questions, please feel free to contact me by phone or email, and you guys have a good day. Thank you.